Welcome once again to your study part. We'll be looking at a continuation of topics which form guidelines to you passing your JAMB examination with regards to the subject physics. As far as today is concerned, we'll be looking at an aspect of physics in relation to gravitational field. And why are we considering gravitational field? It's simply because we know that there are some key aspects under gravitational field which you should get yourself acquainted with, such that when questions come and they are presented to you, you know exactly what to do. Now, these are the guidelines. As far as gravitational field is concerned, there are some certain key parameters which you want to understudy very well before your examination comes near. Some of them include your gravitational force. The next involves your gravitational field intensity. The next, this is also known as acceleration due to gravity. The next is with regards to gravitational potential. Gravitational potential, as well as potential energy. Then we want to pick on escape velocity. Now, these form the key aspects under gravitational field, which you want to put in mind when it comes to preparing for what? Your examination. Familiarizing yourself with these concepts guides you in terms of acing any question channeled at you with regards to this aspect. So, what do we need to put in mind? The first thing is this. As far as gravitational field is concerned, we refer to gravitational field as a region around the Earth where the force of the Earth where the force of attraction of the Earth can be felt, or in terms of any given mass. Would always say that what? It is actually the region around a given mass where the effects, where the pull of the what? The attraction of that particular mass can be felt. So, talking about the Earth, for example, now, let's assume the Earth is here. As far as the Earth is concerned, the region around the Earth where the force of pull, the pull force, where the force of attraction can be felt around the Earth is what we refer to as the gravitational force. So it means that what? When an object is placed at this location, such that the force of the Earth can pull this towards the Earth, then you say that what? That object is located within the what? The field of the Earth. Now, take your mind back to a football field. You expect that a football field is a section divided where football can be played. And one thing is common. Whenever you have the ball out of that region, then you have to carry out what? A duty. There are laid down principles or rules with which you bring in the ball back into that field, such as having to throw the ball back into the field, having to play a corner, having to play a goal kick. So there are rules to bring it back into that what? That region. Now, having said this, we have that what? Under gravitational force. The key thing to note is this. We said that gravitational force in itself is actually the Attraction is the force of attraction that exists between two masses. It exists between what? Two masses which are placed at a distance apart, such that we're able to come up with our law of what? Gravitation, that states that gravitational force Fg is actually directly proportional to the product of two masses m1, m2, and inversely proportional to the square of their distance apart. I repeat again, the law of gravitation stipulates that we have gravitational force being directly proportional to the product of two masses in question and inversely proportional to the square of those what? Masses being apart. So, for spherical bodies, we will always consider the distance as a subject function of their centers. Having this as a center of mass m1, having this as a center of mass m2. We said that what? The distance apart, r, is actually the distance projected from their centers. Now, it's easy to say that we have the gravitational force Fg being directly proportional to the product of the two masses. Note that gravitational force is directly proportional to the product of the two masses, while you have gravitational force inversely proportional to the square of the distance apart. Gravitational force is inversely proportional to the square of the distance apart. Now, having this, merging up this all together, we have that the proportionality sign can always be replaced with what? An equality sign, such that we say that Fg now would be equal to the gravitational constant in this question with regards to the two masses divided by the radius apart, r in this case here now. So this marks the formula we use as far as gravitational force is concerned. Whenever JAMB is going to ask you questions, trust me on this, that what? There's limited attempts to asking you to state gravitational force. Rather, they tend to want you to establish the relationship between gravitational force and the masses. And like we said that what? The relationship between gravitational force and the two masses given in question is such that the gravitational force is directly proportional to the product of the two masses in question. While with regards to their distance apart, whatever mass you are considering, the distance apart, it is such that we consider the inverse proportionality of that distance with respect to the gravitational force. So, as such, we are good to go solving questions under this aspect. We are good to go solving questions under this aspect. Looking at the first question being asked, imagine you being given a question that stipulates that, number one, the gravitational constant is actually given as 7 times 10 raised to the power minus 11 Newton meter square per kilogram. Now, why are we having the units like this? It's actually making reference to G. Remember, we said G is the gravitational constant. When we get to make G subject of the formula, we discover that we cross multiply Fg and R square, such that we have Fg already been equal to Gm1 m2 over R square. When we cross multiply, we have that Gm1 m2, then we have with respect to being equal to Fg R square. And when we divide both sides by m1 m2, we have this cancelling out, such that G becomes equal to F R square divided by m1 m2. And recall that the unit of your force is what? Is actually Newton. The unit of radius, the radius square is going to be meter square, while your kilogram value for the mass is going to be -2. So you have this as your unit. You should be able to place correctly what unit you are going to have subject to the given question. So here is it. The gravitational constant is given as this value. Now, this value exists between two masses of iron and lead such that the mass of lead is 10 raised to power. So let's pick a value which is easy for us to actually punch our calculators with. 10 raised to power 6 and that of iron is 10 raised to power 3. So we have that the gravitational constant 7 times 10 raised to power -11 exists between two masses of iron and lead such that the mass of lead is actually 10 raised to power 6 kg, and you have that what? The mass of iron is 10 raised to power 3 kg. Full stop. If the distance between the masses is 1 meter, comma, determine the force of attraction between them. Determine the force of attraction between them. So how do we go about solving a question like this? Whereby you are given the gravitational constant, you are given the two masses needed for the question, and you are presented with a distance of 1 meter. To solve this should not be a problem for the, with consideration to the fact that what? You can easily manipulate some of these numbers even without the use of a calculator. So what do I mean? To solve this now, we simply say that our parameters given, we have G, capital G, which is the gravitational constant given to us, 7 times 10 raised to power -11 Newton meter square per kilogram square. We have the first mass, M1, as being 10 raised to power 6 kg. We have our M2 to be equal to 10 raised to power 3 kg. We have the distance between them, R value, to be actually 1 meter. So based on this here, we have our needed values complete. We pick our formula, Fg being equal to G, capital G, M1, M2 over R squared. So we say that Fg would be equal to Gm1, M2 over R squared. Fg being 7 times 10 raised to power -11 multiplied by 10 raised to power -6, 10 raised to power 6 multiplied by 10 raised to power 3, all divided by 1 square. And certainly, we have the value here. This guy affecting these two, so we have 7 times 10 raised to power -11 plus 6 plus 3 divided by 1, and that leaves us with 7 times 10 raised to power -2 Newton. That marks the answer to the question. Looking at it, you see that what? It's just a subject matter of indices to follow. It's just a subject matter of indices to follow at this point, whereby we have our -11 adding up with 6 and adding up with 3, and you are good to go with the question. So remember, like I would always tell you, For the fact that we're trying to come to an understanding, a clear understanding of building our accuracy in terms of getting the questions right. That is why I had to itemize what the parameters given are and what the steps would be. When you are solving for your examination, learn to skip some basic steps which you might not be needing along the course. You might be familiar with certain steps which you might not necessarily have to write. So let's try to look at another question in relation to gravitational force. So with regards to this question, the next question, we are trying to establish a basic pattern with which JAMB can ask you questions such that you directly would not have to find the force here. It becomes twisted such that you are asked to calculate the ratio with regards to the question. It might be a subject matter of determining what the ratio is going to be. So have this at the back of your mind that it won't just be a direct question whereby you just have your FG, which is your gravitational force, being plunged into the question using the formula Gm1m2 over r squared. You might have a twist to it in terms of how the question is presented. So look at this one here now. We are told that a planet of mass m1 has a distance of r1 away from the sun. Are you getting it? Now, here is it. A second planet has a mass of 10 m1 and a distance of 2r1 away from the sun. Full stop. Calculate the ratio of the gravitational forces. So we are to calculate the ratio of the gravitational forces experienced by the planet. So how do we go about a question like this, whereby we are giving consideration to two planets this time around, not just one planet, two planets in question. And we are actually asked to compare what happens in the first planet relative to what happens in the second planet. What happens on the second planet? So here is it. As far as this question is concerned, you take into consideration what parameters are given to you. For the first planet, planet A, we are provided with the mass m1, we have the distance from the sun. Mass of planet A is actually this value. Mass of the sun, let's call it m for sun. Then we have the distance of planet A from sun. From the sun. So be equal to R1. On the other hand, for planet B, in the case of planet B, we have that the mass of planet B is actually 10 m1. The mass of planet B is actually 10 times the mass of the first planet. We have that the mass of the sun is ms, and we have that the distance of planet B from the sun is equal to 2R1. So working with these guys here now, you agree with me that as far as the gravitational forces are concerned, we'll relate the gravitational force subject to the first planet, the relationship between the gravitational force between the first planet and the sun, and we compare it with the force of gravity, force of attraction between the planet B and the sun. We're going to have this. Recall that what for planet A, we are meant to have that the force of attraction would be gm1 m2 over r square. For planet B, gm1 m2 over r square. But the radius here is for the radius between this guy and the sun. So let's fix it up. We say that F for the force of attraction between planet A and the sun is going to be with regards to G gravitational constant, mass of the sun, mass of planet A, over the radius, which is the distance from planet A and the sun. For the B part, we have G mass of the sun times mass of planet B divided by the distance of planet B away from the sun. With this now, talking about ratio only means division. So when I tell you that FA ratio FB, I'm making reference to FA divided by FB. I'm making reference to FA divided by FB. FA divided by FB, sorry. That's what ratio means. So bringing on board these two guys, it means that FA ratio FB in question here will be this value here, GMS MA over RA square divided by GMS MB over RB square, such that we have the ratio of FA to FB will be equal to certain parameters remain constant. So let's leave them and flip the orders which we can. We are going to have that GMS MA over, okay, put it in the parameters. MA is given as M1. So we have M1 as the value for MA. Then RA square. RA is R1 square. Divided by, the value for this part will be G mass of the sun multiplied by 10 M1 all divided by 2R1 square. This produces GMS M1 over R1 square divided by, here the 10 multiplying, we have 10 GMS M1 over square of 2 becomes 4, and we have R1 square. When you flip over because of the division sign, we have that GMS M1 over R1 square multiplied by 4 R1 square over 10 G MS M1. So based on this, G and S will cancel out G and MS. R1 square will cancel out R1 square. The M1 value will strike out M1 value. And what we have left will be such that FA ratio FB in the context of things will be the values which we have here dividing each other. And that means we have 4 divided by 10 which here, 2 here, and 5